So, is there any questions? Anything from the homework y'all want to know about? Anything?
You're gonna keep putting more homework.
Yeah.
Ooh, like
Yeah.
I kind of told one day and then like,
Yeah.
basically the
But
next day.
but the question, but the homework is like two questions now or one question. It's light. Yeah. You can just type it in the calculator and click enter. What's up, man? I feel you though. In the beginning though, it was crazy. Like one homework had like 20 questions. Mhm. But the homework was light though, right? It was like, what's three plus four? You know?
Yeah, the first two questions was like, and then the rest of
Yeah.
them was like,
It got heavy.
you got
Oh man. Yo, but you know what? Y'all could come to tutoring and do it too.
I wish I could go to junior high.
Yeah.
You my first class
Every day?
Tuesday, Monday, Wednesday, Thursday,
Got you.
Tuesday, Friday, Saturday, 2 days.
What about on the weekends?
Week.
Yo, I tutor on Saturdays online. Nobody comes.
Wait, online?
Yeah.
Like,
They have online tutoring every single day. But me personally, I'm online on Saturdays. Yeah.
I can get on time.
Yeah, yeah, yeah. Y'all could come through, get your homework done. It only takes a few minutes. You know? All right. So going once, going twice, no questions?
Bro,
Yeah. Unless you got a question, then I'll do one of your questions for you.
I got a question.
Yeah.
We go here.
Yeah. Well, he got his first. Oh, never mind. All right, all right, you up. Go ahead. Yeah. Hmm. You had a good lunch today?
So this is correct.
Hmm?
Try, but I don't know why
Mm-hmm.
spelling us is incorrect.
So it
So
says
it's all the above and it's about 30% and it's 60. What is the problem?
so when I click submit, it says that you have two answers correct and one is wrong.
Oh,
Let's take a look. So I'm sorry I can't show you this on the screen, you guys, but it says in a statistics class with 136 students, the professor records how much money each student has in their possession during the first class of the semester. The histogram below is the data collected. Boom. Right. So we have about 60 students with none, about between 10 and 20 students have $40. Between 20 and 30 students have, wait, I'm sorry, no. Let me say that again. 60 students have between $0 and $10, right? 40 students have between 10 and $20. 20 students have between 20 and $30. About five students have between 30 and 40. About one student has between 40 and 50. And about two students have between 50 and 60. Okay. So it says this histogram, right, is skewed right, is asymmetric, has an outlier, all of the above. It does have an outlier. Oh, I'm sorry. There was one student that had over $100 in their possession. All right. So, this histogram is skewed right. That's true. It is asymmetric. It has an outlier. Yes, I agree with D. The percentage of students with over $20 in their possession. So how many students have more than 20? So this one is about 20. This is about five, one, two, one. Right? So 20 plus five is 25, plus one, 26, plus two, 28, plus one, 29. So I would say about 29 out of the
30.
136 have what you call it, more than $20 in their possession, right? So let's take a look. What is 29 divided by 136? 1 second, let me just verify. Yep, 136. That is about 21%. So I would say B,
What if
on this.
the answer?
right? And the number of students with under $10 in their possession is closest to under $10 would be 60. Yeah, that's right. Yeah, so that's it. Easy, right?
Oh, yeah.
Yeah.
Or big,
No, you're good. You're good.
now it's finally done.
Yeah, good.
Yeah.
Good. All right. Anybody else? Any questions? You have a question? Go ahead. Let me see. You got a question? Nah. Homework. Yeah. Exam two, just let me know when you're ready. That's all. Today? So you can do it tomorrow. Yeah. 1 second.
Wait, you said I'm gonna go take it somewhere else?
All right, just kind of picking up where we left off from last class. So I want to start off with a comment. All right. So when we use the table of the appendix to find the z value corresponding to a given area, remember we're doing inverse normal, right? We usually use the nearest area value rather than interpolating between the values. However, when the area value given is exactly halfway between the two area values on the table, we use the z value halfway between the z values of the corresponding table areas, right? So this is example 7. This demonstrates procedure. However, this interpolation convention is not always used, especially if the area is changing slowly as it does in the tail ends of the distribution. So when the z value corresponding to an area is smaller than -2, the standard convention is to use a z value corresponding to the smaller area. Likewise, when the z value is larger than 2, the standard convention is to use a z value corresponding to the larger area. All right. So basically what they're saying is when I'm looking up um inverse normal, right? Let me go to the formula sheet real quick. Okay. Let's say that I'm looking up a number. All right, I'm just gonna mess with these two numbers right here. Bear with me 1 second. 8 and 6 is 12. Right, so then, okay, so I'm looking right here, right? These two numbers. Let's say that I was looking for an area that was point 0701. 0.0701, right? If you notice, 0.0701 is 7 units away from it is the 0.0708, and then 0.0701 on the right-hand side, it is also 7 units away from 0.0694, right? It's in the dead middle, right? Of these two areas, right? So what you're gonna do is you're gonna take both the z values, right? So we have -1.47 and we have -1.48. You're gonna take both of them and add them together and then divide by 2. So -1.47 plus -1.48, right? Divided by 2 is going to give you -1.475. That's your z value. Whenever the area that they give you is in the dead middle of the distribution. Make sense? No? You remember you also have an option. You can just totally do this on the calculator and then just like write whatever the calculator says. And you'll be 100% right with that. You know? But otherwise, if the area that they gave you, like we had in our last example, 0.0700, if the area is closer to one side than the other, then you just take the z value of the other side. So like negative 1.47 would be our answer to our previous question. All right. All right, so inverse normal, right? So we want to use a table of the appendix to find the z corresponding to the given areas A, right? And remember, the areas for A are going to be between 0 and 1. They are probabilities. They cannot be negative, smaller than 0. They cannot be 1. No, they cannot be like 3, bigger than 1. It has to be in between 0 and 1, right? So we have the left tail case, right? The given area A is to the left of Z. Whenever that happens, right, in both of these situations, just look at the formula sheet and copy what the formula sheet says. You're done. There's nothing more for you to do. But then you have the right tail case. All right. If you have the right tail case, what you have to do is you have to find the complement of the area that they gave you, 1 minus the area, and then that's the area that you're going to look up and get the Z value for. Right? And then you have the center case, right? Center case is really interesting, right? So they're giving you an area, it's in the middle, right? But you can't look up the middle in our table, right? Instead, you got to figure out what the two endpoints are and maybe add one of the endpoints to it so that you can look up the positive Z. And this answer will actually have two answers, right? You're going to have a positive Z answer and a negative Z answer. It's the same thing. If Z is equal to 2, you have 2 and you have negative 2. That's it. All right? Try it. Here's an example. You want to find the Z value such that 90% of the area under the standard normal curve lies between negative Z and positive Z. All right? So you guys could try this. Let me start you off a little bit, right? Hold on 1 second. Oh boy. Give me 1 second. Okay.
But difficult. What if the x is 90% there?
The area under the curve is 90%. So this is your bell-shaped curve. This is negative Z. This is positive Z. And I'm telling you that the area in the middle here is 90%. Right? Right? So I want y'all to find one of these Z's. You have two options, right? You could find the negative Z. To find the negative Z, all you have to do is find the area right here and you're good. Or you can find a positive Z by taking the area on the left, this area right here, and adding it to 90 and then looking it up.
And how I find that area?
You tell me, what do you think that area is?
X?
If in the middle, right, there's an X here and an X here, right? If in the middle is 90, what's that area? Individually though. Exactly.
Oh yeah, because it's in total 100%.
Exactly.
That's true.
Exactly. So now I want y'all to find Z. You could either find positive Z or you could find negative Z. It's going to be the same answer if one answer is positive, one answer is negative, right?
95%, 95.
Right. So if you're going to find positive Z, you're going to look up 95%. If you're going to find negative Z, you're going to look up what? What's to the left of negative Z?
So it would be like 0.65 in the positive.
So this is negative Z right here, right? What's to the left of it? what percent is to the left? 5%, right? So you look up 5% to find negative z. Go ahead, do it, and then I'll verify when you're done. What happened to the wind today? Oh man. Just looking up the area. You use the table. Right here. You're just looking in the middle, and you're trying to find out what the z value is. You can look up either 95%, which is 0.9500, or you can look up 5%, which is 0.0500. It don't matter, whichever one you want to find. All right, just use your formula sheet, just look it up and tell me what you get. What's the z value? Any answers? Anybody? You want to see the question again? No problem. All right. You're either looking up 95% or you're looking up 5%. Anybody? Mm-hmm. Not 3.3. Remember, I'm looking for 5% is 0,500. Mm-hmm. What is it? What's the Z value? Not zero. So this is what I'm looking for, right? I'm looking for the Z value for 0.9500 or the Z value for 0.0500. No. You're either looking at 0.9500 or 0.0500. What's the Z value?
Minus, now you have to subtract 0.9500 minus 0.0500 minus the result. That's it.
Just find me the Z value.
The value?
Yeah. Look in the table and find it for me.
Oh. Oh, yeah, it's further than subtract.
So what's the Z value?
I have to see the table.
It's right there. The yellow paper.
So,
Yeah. Like literally just copy. That's all you have to do. It's the easiest question in the world. Just copy. Normal distribution, Z table. But I wasn't it. All right, look. I want the Z value. So like, let's say that this was the answer, right? The Z value for this is 0.2, oh shoot, is 0.20. So what did you get? No. For example, if the area that I was looking for was 0.5793, the Z value would be 0.20. My question to you is when the Z value is 0.9500, what's the Z value?
1.65.
Let's see.
That is the more close to 95, 0.95, so 5.
So look at this, right? Here goes 9,500. You have 0.9495 and you have 0.9505. 0.9500 is in the dead middle, right? So what do you do when it's in the middle? You're gonna find the two Z values. So you have one of them is 1.64 and one of them is 1.65. You see that? Everybody see 1.64, 1.65? So you're gonna add those two Z values together and then divide by 2, right? That's the answer. All right.
What is the value? 1.65.
Yeah, so you're gonna take 1.64 plus 1.65, divide by 2, and then you're gonna get 1.65 0.645. That's the answer of Z. So on the Z table, let me show you. You see right here? We have all our numbers. 0.9500 is in between these two numbers. Right? Yeah. Hey. Yeah. So you just take the two Z values, add them together, divide by 2. Simple. Right? And then for the other side, for the negative Z, it's just negative 1.645. Simple. All right. Questions on this? Anybody? Good? All right. Let's keep it moving. All right, let's say you don't want to use a table. You want to do it on your calculator. Here's how you do it in the calculator, right? You go to second, then you go to distribution, right? For you, with your calculator, it's gonna be second data, then you go across the distribution, right? Go down to where it says inverse normal, number 3. What's the area that they gave us in the question? They gave us 90%, right? So 90% is like 90 divided by 100. You could put 0.9 if you want to. I'm just trying to make it easy, right? This is a normal distribution, so your mean is 0. Your standard deviation is 1. And let me ask you, right? Looking at this picture from the beginning, where's the area? It's in the middle, the center, right? So you go across and you highlight the center. Click enter, go down to paste. There you go. Same answer we found on the table. Light work. All right. Questions on this? Y'all have two options. You do the calculator, you could look it up on the table. I don't care. Give me the right answer. All right. Y'all doing y'all homework? Just put in the right answer. All right. We good? What I just did? Hmm. Hmm. Yeah. Yeah, you have options. All right, let's look at a guided exercise together. In this exercise, you want to find the z value such that 3% of the area under the standard normal curve lies to the right of Z. So if 3% is to the right, that means that what? 97% is to the left. Remember, I can't look up that 3% because it's to the right, but I could look up that 97% because it's to the left, right? Remember that 97% is going to be about 0.9700. You go to the table and you find the 0.9700 on the table. Let's do that. So I'm on the formula sheet. I'm looking for 0.9700, which is practically right here. I have 0.699. That's practically it. So this works out to be what? Z is 1.88, right? Let's come back. All right. And we're good to go. It's about 1.88. Now it says, go ahead. 9,700, so 0.9700. Yeah. But we don't have 97 flat, but we have 0.9699, which is like 1,000th of a point away from 90.9700. And then you get Z is going to be 1.88. Here's the next question. Suppose the time to complete the test is normally distributed with mu equals 40, sigma equals 5 minutes. After how many minutes can you expect that all but 3% of the test will be complete? You just plug in the 1.88, use those numbers so you could get an answer of 49.4. So you would expect that most of the test will be completed in 49.4 minutes. That's it, using the raw score formula that we spoke about from last class. Not bad, right? And then it says to use a table to find a Z value, such as 3% of the area on the standard normal curve lies to the left of Z, right? Very simple, you could just look that up. 3% is going to be 0.0300. You find that and it's negative 1.88. Simple and done. All right, that wraps up this section. Any questions? Homework is already posted. I accidentally posted it too early, so y'all probably had to look at it already. So no worries. Internet loading. All right, it's gonna be good. It's gonna be good. It's gonna be good. Look at what we're getting into now. As soon as the internet starts working, hook me up, hook me up. All right, now we good, we good, we good. All right, new section, new section. We're gonna be talking about sampling distributions. All right. So a population can be thought of as a complete set of measurements or accounts, right? After existing or conceptual, right? A sample is a subset of measurements from a population. We remember that definition, right? When we compute a descriptive measure such as an average, it takes a difference whether it was computed from the population or from a sample, all right? So a statistic is a numerical descriptive measure of a sample. A parameter is a numerical descriptive measure of a population, right? Throwing it all the way back to like chapter 3 right here, all right? It is important to notice that for a given population, a specified parameter is a fixed quantity, all right? On the other hand, the value of a statistic might vary depending on which sample has been selected, right? So when I have a population, right, the mean is the mean, period, right? There is no, I'm going to run this test again and get a different mean. Like, no, in a population, the parameter is the parameter, the mean is the mean. But if I take a sample from the meat from the population, right? That sample from the population that could vary, right? Because I could take a sample from here, I could take a sample from over there, and get different results, right? So for samples, the statistics can vary, but for parameters, for population descriptions, it is what it is. Period. All right. That's what we talking about. I'm about to hook y'all up right now. I'm giving y'all all the sauce right now. Check this out. Check this out. Y'all can't be confused after this. These are some commonly used statistics and corresponding parameters, right? So here's the measurement. Let's say for the mean, right? The statistics is X bar, right? Which is our sample mean. Our parameter is mu, which is our population mean, right? Let's say we want to talk about variance, right? The statistic for variance is S squared. The parameter for variance is sigma squared, right? Say we're talking about standard deviation, right? The statistic for standard deviation is just S, and the parameter for standard deviation is sigma, right? Say we're talking about proportion, right? Our statistic is p hat, right? But our parameter is rho, all right? This is all that you need right here, all right? An easy way to remember this. If you're looking at a statistic, right? And the statistics variable is in English, X bar, S, P hat, right? Then you know that that's coming from a sample. That's a sample statistic. If the statistic, the description that you're looking at is a Greek letter, mu, sigma, rho, these kinds of things, right? Then you know that you're looking at a description of the population, right? That's it. So Greek, population, English, statistic. Right, y'all about to hear about the wrap up of the class. Ooh, it's gonna be good. All right. So often we do not have access to all the measurements of an entire population because of constraints on time, money, or effort, right? We spoke about that earlier. Sometimes you want to know the population parameter, but there's many variables as to why you can't. It costs too much to get. It's like too many people. Like we don't have enough time to do it because the assignment is due in 2 days, that kind of stuff, right? So we must use measurements from a sample instead. In such cases, we use a statistic such as X bar, S, or P hat, right? To make inferences, remember we talked about that word before, to make inferences about a corresponding population parameter, mu, sigma, or rho. The principal type of inferences we'll be making are the following. Before I go into that, remind me, what was an inference? If I'm making an inference, I'm making an educated guess, right? Educated guess, right? So here are our type of inferences that we have, right? So we have estimation, right? That's going to be the next chapter that we go into. In this type of inference, we estimate the value of a population parameter. Two, we have something called testing, right? This is going to be our last chapter for the class, right? In this type of inference, we formulate a decision about the value of a population parameter. So literally, testing is how you make decisions, all right? And then we have regression. We already spoke about regression, if you guys remember. That's when we were plotting the points and making the regression line, We already did that, right? So in this type of inference, we make predictions or forecast about the value of a statistical variable, right? So y'all ever want to know how to make money? Regression, right? Hashtag that's why we don't gamble. All right. So to evaluate our reliability of our inferences, we will need to know the probability, right, distribution for the statistics we are using. Such a probability distribution is called a sampling distribution, right? And then perhaps chapter example 9 will help clarify blah, 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 right? A sampling distribution is a probability distribution of a sample statistic based on all possible simple random samples of the same size from the same population. All right, let's look at one. Let's look at an example. Oh boy, this is gonna be dope. This is gonna be dope. I gotta bear with me for 1 second though. Bear with me for 1 second. Yeah, just bear with me 1 second. Do, 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 do. Yeah, life ain't good without a table, man. We need that table. That's how we do it. This is how we do it. Let me stop. Oh, yeah. All right, let's get into this real quick. All right, sorry if anybody was copying. So sample distribution for X bar, right, for our sample mean. Pinedale, I think that's how you say it, Wisconsin, is a rural community with a children's fishing pond. Posted rules state that all fish under 6 inches must be returned to the pond. That's because they babies. You know, you always throw back the babies, you want some adults. All right, anyway. Um, only children under 12 years old may fish, and a limit of 5 fish may be kept per day. Right? So we go to the fishing pond, you could get 5 fish, and then you could bounce. That's it. All right. Susan is a college student who was hired by the community last summer to make sure the rules were obeyed and to see that the children were safe from accidents. The pond contains only rainbow trout and has been well stocked for many years. Each child has no difficulty catching his or her limit of 5 trout. All right. As a project for her biometrics class, Susan kept a record of the lengths to the nearest inch of all the trout caught last summer. Hundreds of children visited the pond and caught their limit of the 5 trout. So Susan has a lot of data, right? She made a table, right? And you can see that Susan selected 100 children at random and listed the lengths of each of the 5 trout caught by a child in the sample. Then for each child, she listed the mean, length of the 5 trout that the children caught. Here's a table of what she did. All right, so this says length measurements of trout caught by a random sample of 100 students in the Pinedale Children's Pond. Let's talk about the first row real quick. All right. So this is the first sample. That's why it says sample one. All right. So this is like child number one, for example. These are the 5 trout that that child caught, right? One was 11 inches, 10 inches, 10 inches, 12 inches, 11 inches, right? She took the 5 trout that that child caught, and she did a mean of it. She added them together and divided by 5. That comes out to be 10.8. That's the average size of the trout that that one kid, right, caught, right? Okay. Now, do that same idea 100 times. Now you have her table. All right. So we have a mean for 100 kids. Okay. Now let's turn our attention to the following question. What is the average mean length of a trout taken from the Pinedale Children's Pond last summer. So we have a mean for every single child, but we're not interested in what the one child did, right? We're interested in what is the mean for all of the children. Well, let's see what we're gonna do. Little blast from the past, right? We're gonna make a frequency table. Yeah. Let me show y'all. I don't feel like doing this out by hand because of time. I'm just gonna show you. You can copy if you want. Yeah. All right, so here goes our frequency histogram, right? So we can get an idea of the average length by looking at the far right column, right? So on the right, all these numbers, this is our average means, right? Our sample averages, right? But just looking at 100 of the X bar value, sample means values doesn't tell us much. Let's organize our sample means into a frequency table, right? So we made a frequency table and we had a class width of 0.38 to make the table. Here you go. You guys remember how we make the frequency tables, right? You find the smallest mean, right? Then you do the class width, right? And then the smallest mean is going to be here. Add the class width to it. Boom, boom, boom. Right? Class width at the end for the larger ones, etc., etc., etc. We remember this. All right. Now, the frequency here, this is the number of children that caught a trout between these lengths. 8.39 and 8.76, 8.77, 9.14, etc. We remember that, right? The relative frequency, remember how we find that? We just take the number of children that fell into this class and you divide it by everybody, right? So this is like 1 divided by 100, 0.01. Next one is like 5 divided by 100, 0.05, etc. Cool? All right. So no techniques in section 2.1 dictate that the class width that should be of 0.4. However, this choice results in the 10th class being beyond the data. Consequently, we shorten the class width slightly and also started the first class with a value slightly smaller than the smallest data value. All right. The far right column of table 7.9 contains the relative frequencies. So we're talking about this part right here. All right. Recall that relative frequencies may be thought of as probabilities. So we effectively have a probability distribution because the X bar represents the mean length of a trout based on the sample of 5 trout caught by each child. We estimate the probability of a sample mean falling into each class by using the relative frequency, right? So that figure is a relative frequency or probability distribution of the sample means, right? The bars, right, in the histogram, right, will represent our estimated probabilities of sample mean values based on the data from the table. The bell-shaped curve will represent the theoretical probability distribution that would be obtained if the number of children, right, were much larger. Central limit theorem. All right. Let me show y'all what we mean. I'm gonna get that for you. Nickelodeon. All right. So as you can see, we have our distribution right here. We have our histogram, right? We have our class widths on the bottom, relative frequencies on the side. This red line that you see here is representing our normal distribution curve. Had we had more children in this study, say instead of 100, we had like 1,000, excuse me, or like 10,000, for example, right? That would give me more bars underneath this distribution. And you will see that eventually the bars will fit perfectly under that red line, right? So as the sample size grows larger, right, the distribution becomes more and more normal, right? That's the idea. So this figure represents a probability sampling distribution for a sample mean of Trout's lengths based on random samples of size 5. We see that the distribution is mouse-shaped and even somewhat bell-shaped. Irregularities are due to the small number of samples used, only 100 sample means, and rather small sample sizes, right? 5 trout per child. These irregularities would become less obvious and even disappear if the sample of children became much larger. If we use a large number of classes in the figure, right? And if the number of trout in each sample became larger, meaning that Susan, instead of she just looking at the 5 trout that Johnny has, maybe she looks at what Johnny caught for the week, right? Monday was 5, Tuesday was 5, Wednesday was 5, Thursday, Friday, and then we use that information. That's what they mean right there. In fact, the curve would eventually become a perfect bell-shaped curve. So we will discuss this property some in the next section, which introduces the central limit theorem. Very cool, very cool, very cool, very cool. All right. Sharing the sauce with y'all right now. So there are other sampling distributions besides the sample mean distribution, right? In the next section, we're going to shows the sampling distribution for p hat, right? In the chapters ahead, we will see that other statistics have different sampling distributions. However, the sample mean sampling distribution is very important. It will serve us well in our inferential work in chapters 8 through 10 on estimation and testing, right? Very cool, very cool, very cool, very cool. All right. So putting this all together, and yes, you guys have the homework posted for this. It is just some multiple choice questions, all right? Just some vocabulary, no math in this homework, right? So what does a sampling distribution tell us, right? That's the $50 million question. So sampling distribution gives us information regarding sample statistics such as the sample mean X bar or p hat, right? Which is our proportion, right? For the binomial distribution. The sampling distribution is based on values of the sample statistics from all samples of a specified size n. Sampling distributions are used to obtain information about corresponding population parameters, right? In the next section and chapters, we will see how to obtain information about the value of a parameter mu from a sampling distribution of X bar. We will also study sampling distributions of p hat, the sample probability of success in the binomial trial. All right? Good stuff, good stuff, good stuff. Questions on this so far? All right, let me introduce y'all to a new idea. And we're probably not going to finish this idea, but we'll pick it up tomorrow. This is going to be fire right here. All right, so the central limit theorem. Here it is. All right, the central limit theorem. So this is the X distribution given that X is normal. So in this section, we begin a study of the distribution of X bar values, right? Sample mean values, where the sample mean was the sample, right? Mean length of trout caught by children in the Pinedale Children's Fishing Pond. Let's consider this example again in the light of a very important theorem in mathematical statistics. So here you go. Here's the theorem. For a normal probability distribution, let X be a random variable with the normal distribution whose mean is mu and whose standard deviation is sigma. All right. Let X bar, the sample mean, be the sample mean corresponding to the random sample of size n taken from the X distribution. Then the following is true. A, the X distribution is a normal distribution. B, the mean of the X bar distribution is mu. And C, the standard deviation of the X bar distribution is sigma divided by the square root of n. All right? There's your theorem right there. All right. So we conclude from the theorem that when X has a normal distribution, the sample mean distribution will be normal for any sample of size n. Furthermore, we can convert the X bar distribution to a standard normal Z distribution using the following formulas. Oh boy, this is sauce right here. So you have the mean for the X bar distribution, which is equal to mu. The standard deviation for the X bar distribution, which is equal to sigma over the square root of n. Putting it all together, we have a new Z formula, right? So Z is equal to the sample mean minus the population mean for X bar divided by the standard deviation for the X bar distribution. Putting that all together, it becomes X bar minus mu over sigma over the square root of n. That's your new Z formula. And guess what? I got good news for you. Good news for you, right?
You do this in the calculator.
Huh? Yeah. It's on the formula sheet. Yeah. I wanna show you guys it though. Yeah. So if we look at our formula sheet, right? We gotta like turn to the front to the first page. So when we're on the first page, right, for our formula sheet, go down to where it says chapter 7. And there you go. You have the mean for the X bar distribution right here. Mm-hmm. Mm-hmm. And then we have the standard deviation for the X bar distribution. And then we have our standard score for X bar. Here's the formula right here. That's all you need. Go ahead. Mhm. Right. The previous question that we had, it didn't have a sample, right? N was 1. But in these questions, we have a sample. That's the difference. Yep. We're using this formula right here for the standard score for X bar. All right. So yeah, that's the difference right there.
Some of your homeworks have that already.
Exactly.
So I did that.
Yes, awesome.
So
You know? Yeah, I accidentally posted it too early, so that's why. You already have the
on the other.
It's the same thing.
Yeah.
The same thing. The only difference is that you have this divided by the square root of n. Same formula, same everything. All right. All right.
And
So
sometimes you have to put one minus, right?
yeah, when you're looking it up. Yeah.
When you look,
Yeah.
one minus the result and that.
Exactly.
Because I made it and then it was wrong and.
And then you
they
did one
told me
minus,
Minus the result.
and then you're
it was
good,
Good,
right? Whenever it's greater than.
yeah,
Yeah.
exactly,
Mhm.
yeah.
All right, so n is our sample size. Mu is the mean of the X distribution, and sigma is the standard deviation of the X distribution. All right. All right. It's on the formula sheet. Yeah. Yeah, no memorization. For your calculator, if you want to use it, you're gonna have to memorize it. That's different. All right, theorem 7.1 is a wonderful theorem. It states that the X bar distribution will be normal, provided that the X distribution is normal. So the sample size n could be 2, 3, 4, or any other fixed sample size we wish. All right. Furthermore, the mean of the X bar distribution is mu, same as for the X distribution, but the standard deviation is sigma over the square root of n, which is, of course, smaller than our traditional sigma. All right, so let's look at an example. All right, so probability regarding x and x bar, right? Suppose a team of biologists have been studying the Pinedale Children's Fishing Pond. Let x represent the length of a single trout taken at random from the pond. This group of biologists has determined that X has a normal distribution with the mean mu equal to 10.2 inches and the standard deviation equal to sigma, which is 1.4 inches. What is the probability that a single trout taken at random from the pond is between 8 and 12 inches?
You need to start with the sigma and this time, with no with the
So do it. I'll give you guys a few minutes.
The other, you're supposed to start with the mean first. In
Mm-hmm.
this case, you always start with. So that's your.
Mm-hmm. Try it. Go ahead. I just highlighted the important parts for you. I'll give y'all like 4 minutes. I haven't gotten to the new part yet. This is a review of the old part. So you use the old formula, not the new formula that I just showed you. And how do I know to use the old formula? I have a single trout. Try it, try it, try it.
So you are using a standard score formula, right?
Mm-hmm.
So, got a question.
Go ahead.
So you will say 8 times 1.4 over 10.2, right?
Mhm.
No,
X minus the mean divided by sigma.
or x minus the mean divided. Oh,
Yeah.
oh. And this time, what is x? 8? Each shoulder.
X,
Whatever.
there's two X's. X is 8 and X is
Then
12.
12,
Yeah.
right?
Mhm.
8. Amen.
You're wondering about yesterday, like it literally just finished downloading. My fault. That's why I haven't posted it. All right. What's the answer?
90. Alright, so I got for 8, 0.65, and for the other one, 1.04. So now I have to look at the area. No,
Those are the areas. But what do you do with those two numbers? You're really close.
-1. 1
Not
minus
no, not one minus. This is in the middle. What do we do when it's in the middle?
in the middle.
Not add them, but you're close. Something else.
Multiply.
Subtract them,
Plus subtract.
and that's it. All right, that's it. Not negative. The answer has to be positive because of probability. No, not 8 minus 12. You subtract the probabilities from one another. All right, so look,
How I do it? 0.65.
the calculator is whatever it is minus the other one. That's it.
Okay.
Yeah.
Oh,
So look, what they're looking for, they want to know what's the probability of 8 less than x less than 12, right? Now, you know we can't look up in between in the calculator, so I'm going to break it up from the beginning. This is going to become probability of x less than 12 minus probability of x less than 8, right? Remember, you always do the big minus the small, right? The big minus the small. All right, right after that, you know we got to switch this into a z, right? This becomes probability of z less than x minus mu over sigma minus probability of z less than x minus mu over sigma. After that, just plug it in. Keep it simple. So this is going to become probability of z less than a. I was about to say something wrong. 12 minus the mean, which is what? 10.2 divided by the standard deviation of sigma, which is what? 1.4, right? If you're wondering where did I get those numbers from, it's in the story right above. Look up, it's highlighted. Minus the probability of z less than, this is 8, minus the 10.2 all over the 1.4. After that, a little bit of calculator and we good. This becomes probability of z less than, what did you get for the first one?
0.65.
0.65? That might be right. Yeah. It might be right. Let me check it. It should be positive because it's positive 12 minus that. All right, let's take a look. Let's take a look. So I got 12 minus 10.2 divided by 1.4.
Although you don't start with the, you don't start with the with the standard deviation here. You started with the, so because I
With the
I said
numerator.
8 minus oh
With the numerator, yeah.
oh.
So I got 1.29 when I did it. Minus probability of Z less than, now this is what? This is 8. You got 1.7? It should be negative. Yep, negative 1.57. That's right. All right. And then now you just go to the table, look it up, subtract the two answers. I'm looking for 1.29, right? Let me look. Okay. So we're gonna look it up in the table. What is 1.29? Mm-hmm. Mm-hmm. And that's the end of the question. Right? So I got a positive 1.29. So I'm going to come down to where positive 1.2 is. Look, here goes positive 1.2. Here's the 9 up here. It's the last column. So 1.2 going straight across is 0.9015. Everybody see how I got 0.9015? Any questions about it? Right. We need two decimals whenever we're looking it up, right? The next number after the 8 was a 5, so it becomes 1.29.
Yeah,
Right.
1.29.
Right. So we have
So-
0.9015.
So and then you look at 1.2 and then 0.9, right? And the table.
1.2 is 0.9, right? You know
Yeah.
where they intersect that.
And then that is the answer.
Yep, you just write it down. That's it.
And then
Oh, wait, I'm not showing you that I wrote it down.
1.5 and then
Mhm.
0.7 and that's the
Yeah,
answer. Okay.
and that's it.
All right.
That's my fault. I didn't show you that I wrote it down. See? And then after that, I'm going to look up negative 1.57, right? So you go to the negative table, you go to negative 1.5, which is right here. Here goes the 7. We're looking at where they intersect that, and they intersect right here. This is the 0.0582, right? 0.0582. Let me write that down. So 0.0582. After this, a little subtraction. That's it. We're writing the calculator. You got 0.9015 minus 0.0582. Boom. So now we have our answer, which is 0.8433. Go ahead. The area. Mm-hmm. Huh? Mm-hmm. Mm-hmm. So look, if I had a distribution like so, right? Let's say that this was 0. Right here, this would be the 1.29. And over here, this would be the negative 1.57, right? I want this area in between here. That's what I want, but I can't look that up. So what I do is I take the area from the big one, which is the 1.29, which is all of this, and I subtract it from the little area. This is the negative 1.57. This I could look up. And then that's how I get the final answer of 0.8433. That's it. What happened? Mm-hmm. Like how to look them up? The area under the curve, yeah. So this is, huh? The Z values? Because that's not the area. The Z is the number of standard deviations away from the mean that a number is, you know? Yeah, we subtract the areas instead. Right? And then that's how we got our answer. Cool. Now, real quick. I know we out of time, but real quick. Say you wanted to do this in the calculator. Pretend that you're standing in the distribution like so. Whatever is to your left is your lower bound. Whatever is to your right is your upper bound, right? And then you just go straight to the calculator and do it. Let me just show y'all real quick. I'll be quick, I promise. So here we go, right? So what you want to do, you want to go to second distribution. If you have the TI 36X Pro, it's second data, then go across to distribution and go down to normal CDF, right? Then they're going to ask you for these four things. They're going to ask you for lower bound, upper bound, mean, and zero. Your lower bound is the negative 1.57. Your upper bound is going to be the 1.29. Your mean is 0. Your standard deviation is 1. You paste it, right? Carmen, for you got to memorize this, right? Remember that? So we're going, for you, Carmen, this is equal to normal CDF, lower bounds, upper bounds, mean, sigma, which becomes normal CDF negative 1.57, comma, 1.29, comma, 0, comma, 1, close parentheses, right? Then you hit enter in the calculator, gives you the answer straight, 0 point, listen to me, 0.84326704333. Y'all know I don't like to round, right? But same answer that we got above. That's what matters. All right. Questions on this? No? All right, that's it for today. Please sign out before you leave. Huh? You want to see this?
Yeah.
Wait, let me hold on, let me do this real quick. This way you can see it a little bit better. Appreciate it, man. Have a good night, man. Here you go. So you can see everything. Welcome. Bye. See you. All right. I can take this down now?
Yeah.
Awesome. Thank you. Appreciate y'all.